2012 E&M number 1. This is an electrostatics problem, and they gave us two concentric spherical shells with noted radii and voltages. This means that they are indirectly telling us what the charges are on these guys, because we can use the point particle and the voltage from a point particle to figure out what the charge is. And that's what they're going to have us do, starting out with Gauss's law, to figure out some expressions here. So for part A, they say derive an expression for the electric field, and they're telling us, at the beginning anyway, that the charges are going to be Q inner and Q outer. So starting with Gauss's law, Q enclosed over epsilon naught equals integral E dot dA, and we're going to need to choose our Gauss's law to be a sphere, and it will be centered with the other guys, and the radius will be between 0.1 and 0.2 as they tell us here in the instructions. So our surface area of a sphere will be 4 pi r squared, and the Q enclosed for this one is just going to be the inner one. So this will be Q sub I. Substituting both of these guys into Gauss's law and solving for the electric field, we get the inner charge over 4 pi epsilon naught, and then 1 over radius squared. For part B, they're going to say, how about we do the same thing except outside the outer sphere? So that's going to change the charge enclosed to be including the outer charge, which means our electric field expression is going to change only a little bit to include both charges, but otherwise it stays the same. This is because, oh, wait a second, that should be an epsilon naught here. That's because these are conducting spherical shells, which means that all of the charge, the inner charge, is on this ring here, and all of the outer charges on that ring there. So when we move from between to outside, we're only including that extra outer charge. There's empty space in between these two shells here, so it's not like we're filling it up as we do in other questions where they give us non-conducting spheres where the charge is spread out. All right, part C. How about we figure out the electric potential, and they want us to be outside. So the electric potential outside, so change in V is going to be integral E dot dr, and we have an expression for E as a function of R, so we can use that. And in this case, let's start out very far away. So remember what we did in class. We put all the toys away, all the pluses and minuses charged, and then we brought them in one at a time. And then when we were going to figure out what the electric potential was, we took our tiny little positive test charge from infinity and we brought it into a position R away from our spheres. So we're going to start out very far away, and we're going to come into a position R. That's an R. So we're going to substitute into our integral Qi plus Q naught over 4 pi epsilon naught. Those are all constants. And then we will have our variables here, dr over r squared. And when we integrate these things, we're going to have a 1 over r with a minus sign. So this minus sign is going to go away. And our overall expression is going to be Qi plus Q naught over 4 pi epsilon naught, 1 over r, and don't forget that you need to evaluate your limits. In this case, the infinity, or increasing without bound properly, means that the whole expression goes to 0, and we have our expression here as Qi plus Q naught over 4 pi epsilon naught 1 over R. And again, this infinity means that the voltage is going to be 0, so we don't even need that. All right, part D. Using the information given, find the total charge on those two shells. Now they tell us that once we get to the outer shell, we're at 100 volts right there. And they also tell us the radius. So we can come here and we can say, hey, the voltage is going to be, for part D, that voltage is going to be 100 volts. And our Q total is the sum of those two guys. Number, constant of the universe that you can look up. And then right on the outer shell, we have a radius of 0.2. So plugging in all of these numbers to our calculator, we can get the total charge to be 2.22 times 10 to the minus 9th coulombs. All right, I'm going to have to pause here and scroll things up. And I'm going to hang on to, or what I want to hang on to is our expressions for the electric field, and then also for the voltage, because we're going to make a couple of graphs. All right, let's make a couple of graphs here. And as guides, just for the shape of the graphs, we're going to take a look at our voltages and our electric field expressions here. So let's start with the voltages, because they gave us numbers where that's concerned. So they gave us negative 100, and they gave us positive 100. And that positive 100 starts at 0.2, and that negative 100 is at 0.1. Now, for conducting shells, where all of the charge is on the outside, that means that the electric potential is constant inside the shell. So that dot should be right on negative 100. When we get to a radius of 0.2 in the outer shell, we'll be at a voltage of plus 100. And what we're going to have is a 1 over R kind of sweeping curve from the radius of 0.1 to the radius of 0.2, but it's going to be concave down. So it's a 1 over R kind of curve, but it's concave down. And then we get to a 1 over R kind of curve on the outside that's concave up. And both of those come out of this expression right here. So we're moving away from a negative charge towards a positive charge, but it's a 1 over R. So it starts out negative and then ends up positive. Once we get to a radius of 0.2 and we've enclosed both of the charges, now we have an overall positive charge here, which we found in part D, and it's going to be a 1 over R relationship. Now, the electric field is the derivative of the voltage. So if you remember, electric field is the spatial derivative of the voltage, and they give us a space dimension here for our x-axis. So if we take the derivative of 1 over R, we're going to get a 1 over R squared kind of relationship. Or we can take a look at these three sections here and ask ourselves, what does the slope look like for each of these three sections? So for the first one, the slope is 0. So the electric field inside a conductor is going to be 0. That should be exactly on the x-axis, and I'm having a little trouble drawing it. Now, when we're near the negative of the negative charge, we're going to have a negative electric field. It's going to be pointing towards the negative charge. So our negative electric field is going to be a 1 over R squared kind of thing, except it's going to be negative because the inside sphere is a negative charge. Then for the outside, we're going to have the same thing, except it's going to be positive. and it's also going to be a 1 over r squared. Since we have spheres here, the electric field is going to be a 1 over r squared kind of relationship. And we're going to be jumping because these are conductors. So when you go from inside to outside, all of a sudden there's a change. When you go from inside to outside, all of a sudden there is another change as we've now included more charge.